Something very cool happened to me last week and I wanted to share it. This might inspire you to take on this challenge. It might also benefit you in your research or in your machine learning journey. I'm a graduate computational physics student and I write a lot of code. In this video, I will tell you how I sped up my research with a GPU accelerated code. I did it by writing custom GPU kernels. They handle the heaviest computations in my code, making it much faster. A CUDA kernel is just a function that can run only on a GPU, and it has a special way of indexing the arrays that it works on. Even though I have done it in Julia, you can also do it in a very similar way in other languages like Python or C++. The logic is the same. In fact, I had to also read some of the official CUDA C++ programming documentation to get some of my code working, because really it is the most comprehensive documentation out there. Even though Julia has a decent amount of documentation on their website at CUDA.jl, still for many cases it refers directly to the official CUDA documentation. So since I'm working in Julia, the only difference I had to watch out for is the fact that indexing is Julia is one base. And another difference is obviously some minor differences in the syntax. So a couple of weeks ago, I hit a critical point. I felt frustrated and pressured by the looming deadline of my master's thesis, which is due in only 7 weeks from now. And I figured that the best thing I could do at the moment to help me write my thesis faster is to make my program run much quicker so that I can accomplish more in a shorter time and collect the data and analyze it much faster. When writing my thesis, I sometimes need to check something really quickly in order to support any claims I'm going to make. And the way I do it is by running simulations, but with a set of changed parameters that fit the question. But the calculations took days to finish with the old code I had. I'm running Monte Carlo simulations, and the number of Monte Carlo steps you take per data point is very important if you want to get quality data. So if the code is slow, the only way to shorten the runtime is to cut on the number of steps, which is not what we want, because we might end up with the data that shows the system which had not enough time or steps to equilibrate, and that way we will be analyzing maybe some artifacts of non-equilibrated system. And so making the code run faster is the only way to make a quality change to the program. So since my code is only a tool that I use in my research, and if the tool is of a poor quality, well, if it's slow, my work suffers. Getting the data takes longer. I can't start writing anything until I finish the data collection and analysis. My productivity suffers with the slow program. So a couple of weeks ago, I decided to go all in and put all my effort into making my program run as fast as possible. I must say that my old program that I call old used also GPU programming, but it was the so-called GPU array programming, which is different from the kernel programming. And if you would like to look into the difference between both of these types of the GPU programming, I'll leave the links in the description so you can go and check it out for yourself. So I worked on this task for about 10 hours over the course of a week, and I had moments where I was about to give up and just keep using my old code, which was slow, but it still was useful, and my brain was on fire. But at the end of the day, like after about a week, I had a breakthrough, and it made such a big difference. Now my code is blazing fast compared to what it used to be. So the obvious tangible benefits that fast program can bring you is that, well, you get more productive. You can get more time on your research, on doing other meaningful tasks, learning new things. If you can finish those work-related tasks sooner, you can free up time for your other personal projects. I don't know, leisure time, reading, whatever suits your fancy. There are also intangible benefits to it. It can bring you a great sense of accomplishment once you get such a complicated thing working. And I understand for some of you it might not be very complicated, but I struggled with it for a while until I wrapped my head around on how to do it. And it worked. Sense of accomplishment can really be another big benefit to something like this, because it just shows that you hit another breakthrough, which is a great feeling, I must say. In a little while, I'll show you the timings for each program version, but it still might not be the best possible performance I could get. I just don't have enough time to do a detailed profiling on this code and see where the potential bottlenecks are, but this is good enough for the rest of my master's program. So writing the GPU kernels to handle heaviest computations of your program can bring a big benefit, but this is not the only way to improve your code performance dramatically. I discovered something which can bring another good speed up, very good speed up, without having to code anything, and I'll share it with you in a moment. First, I will give you some tips on where to start if you want to learn GPU kernel programming. It's not that difficult, don't be afraid. So first of all, look up how the block and thread indexing on GPU works. What are blocks, threads, which computations they handle. It's very important, and it's probably the most difficult part in all of this. You might not fully understand it initially, and that's okay. I did not either. To help with that, start with very simple kernel functions that are provided in the official documentation. Try to run them, try to understand them line by line, what they do, how the indexing there works, what is the logic behind it, what goes in, what goes out of these kernels. And this should help you a lot in understanding how the indexing works and overall logic behind these kernel functions. Also, it's often very useful to leave it be for a little while. Maybe days, maybe weeks, maybe even months like I did. This was my third attempt at this. The next time you get back to it, it should make more sense. It will. And after you got the basics down, the best way to learn is to apply what you've learned to your own project, because in this case you know what your program is supposed to do, what your calculations should look like, and that way you can compare the results from your GPU accelerated code with the results of your other, maybe not even parallel code that you know the results of. For example, I have a few test cases where I really know what the results should look like for my specific program. If I run the simulations with both versions of code with these parameters, ideally the results from both programs should match up, and if they do, it's a good indication you got it right. In my opinion, the most difficult part is to get the indexing right. To make this part easier, plan ahead before you start writing the code how your arrays that those functions accept should look like, what should be the layout of the arrays or matrices, and how they will be mapping onto the GPU. Because in the block thread structure, each block is a group of threads, and each thread can access only a single element in a matrix. And that's usually the way to do it, as far as I understand. So it really helps to think through the layout of your data ahead of time before starting to write any functions. Also, your program, the overall program, can have more than one kernel that handle computations. If the computations of a different type or the arrays of different sizes, you can write more than one kernel and then call them to do those computations. And that's what I did. So that's also something that you can keep in mind when trying to design your program. And one last final tip I have for you, you can try using ChatGPT as well. I must admit that I also used ChatGPT occasionally to help me sort out the indexing right. I would tell it what my input arrays look like, what calculation needs to be done, and then what the output arrays should look like as well. And then it will help me to set up the indexing correctly. Sometimes it can get it right, sometimes it gets it wrong. But nevertheless, often it gives you a really good direction. In any case, if you use ChatGPT to help you with this, the key here is that you should have a pretty clear idea of what your results should be so that you can see if the suggestion makes sense or not. So despite its shortcomings, ChatGPT can be really helpful, but paired with the official documentation and a little bit of common sense, it can get you a long way. Remember, I told you there is one more thing that can help you to make your code even faster, but without any coding. So here it is. So when I'm writing my code, I'm using my workstation at uni to prototype it, usually in VS Code and Jupyter Notebook. And so I write the code there, test it there, and then open the terminal and run it, because my workstation has 2 GPU cards. So when I was done with that new improved version, I tried to time it, and I already saw a relatively good performance increase. I mean, it was only about 2 times faster than the previous version. And I was initially slightly disappointed, but 2 times faster, it's still better than nothing, right? And then I tried running it on the HPC cluster, or high performance computing cluster, which has many nodes with GPU cards available to us, and I needed to run multiple copies of that program just with the different set of parameters so they can have different simulations, and running it on my workstation wasn't workable. So I had to start them all on the cluster, and to my big surprise, when I ran them there, they were incredibly fast. And I still don't know why. What happened there. Probably it's something about the memory management, but I didn't have time to check it out. So if you have any ideas, feel free to leave the comments. But here are some timings. My old code, if I quickly take a look at about 3000 Monte Carlo steps over the whole program run. It took me about 720 seconds. Then the improved version on my workstation took about 480 seconds. Not quite 2 times faster, but still faster. And then the run on the cluster of the same program for the same number of steps takes only 30 seconds. It's like 25 times faster overall compared to the old version. And I'm just amazed at how much difference it made just running that same script on the HPC cluster. Now I can take all my data within a day, even within a couple hours if I want to. Now, if you feel compelled, go ahead, get out of your comfort zone and try writing your own GPU kernels and see if that brings you any benefits. As Stephen King said, the scariest moment is just before you start. If I was able to do it, so can you.